So today we're going to continue with what we've been talking about. So eigenvalues, eigenvectors, and solutions. Of ODEs. Okay, so the goals are, so the objectives. So these are, well, understanding eigenvalues and eigenvectors. So and eigenvectors. And so this is something from linear algebra that you used in an ordinary differential equations class in usual ODEs. And so mostly with constant coefficients. So, so one of the mottos is, so this is kind of a idea that expanding in terms of eigenvectors makes things easier. And it actually like decouples problems that are like coupled. Okay, so all right. So let me just I'll give you the diagram of what we've been doing here. So we've taken so like the general strategy. Right, was that for solving an ODE. An ODE, or finding the general solution of an ODE with constant coefficients. Right, so we'll have our differential equation here. So we could have something like this. And then we could have something like A0, y, this is equal to 0. So we have this linear differential equation, right? And what we do is we find this characteristic equation associated to it. Here you get m to the n, or lambda to the n, here. So A0 is equal to 0. So this is a polynomial in M, I guess. So this is a degree n polynomial. Sometimes this is used lambda here. And so for simplicity, we'll assume all the roots are distinct, so no repeated roots, no repeat roots. Right, so we did this before. So in our example, our particular example was, we did y prime prime plus 2y prime plus y is equal to 0. So this is like our particular thing. And then here, the equation that we'd get is m squared plus 2m plus 2 is equal to 0. All right? Okay, so once you have that, so then we'll get a solution that looks like y of t looks like c1 e to the m1t plus c2 e to the m2t plus cn e to the mnt. Okay, so here, here we're using this thing A0, so this is equal to m minus m1, m minus m2, m minus mn. So these guys are the roots. The mk are the roots of this. And so this gives us a solution with complex coefficients. And then to get the solution with real coefficients, right, if you wanted something with real coefficients, you use Euler's formula, right? So the real solutions, we use Euler's formula. Okay, and then the observation is, okay, so where is the eigenvalues appearing here, the eigenvectors? So we note that we noted before that this e to the m, let's say e to the lambda t here is equal to lambda e to the lambda t. So this is the operator, and it spits out a lambda in front of it. So this is an eigenvector. Eigenvector or eigenfunction. And then this thing here is the eigenvalue. So let me say something else. So we showed that those are solutions. Those are also all the solutions. How could you show that there are also solutions? So one thing you could do is to show that all solutions look like this, is you could look at the initial value problem, right? So are these all the solutions? Right? So let me just say this quickly, is that so you can consider, so here's the question. The answer is the following. So we can consider, so let's say given y of t, any solution of the ODE, right? Let's say it's an infinitely differentiable solution so that I can take derivatives of it, right? We can consider here so sorry, y0, y prime 0, so dot 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 y to the n minus 1 of 0, like this. And so these are particular values. So I guess we could call these, I don't know, S0, S1, S2, Sn. Okay? And so these things here, so these allow us to solve for the constants. So C1, Cn in the general solution. Do you see how this works, right? I plug in, so I can take this thing, this guy here. If I plug in 0 here, right, I'm going to get this thing. So I'm just going to get the sum C1 through Cn, okay? And that's going to be equal to S0. If I take the derivative, these m's pop down, right? And I plug in, then I'll just have MC1, MC2 when I plug in 0. Do you guys see that? So on, And you can keep doing that. If I do that n times, I'll get n equations and n unknowns, right? So these things are known. They're given, right? And these things are the unknowns. So I can solve for the c. So this means I can find a solution like this, right, which satisfies this thing. Okay? And so the claim that you need to do is to check the following, is that if we put zeros everywhere, so okay, so by taking derivatives of this thing, C1 MNT, and using the initial conditions, this thing here, star, we get n equations and n unknowns which allow us to solve for the C1 through Cn. Okay, this is not enough yet. Okay, so let me show you the system of equations. The system of equations looks like this. S0 is equal to C1 plus C2 plus Cn. S1 looks like lambda 1 C1. I use M1. M1 C1 plus M2 C2. Mn Cn. And then I could keep going. Sn. So I guess I got Sn minus 1 looks like this. It's equal to M1 to the n minus 1 C1. Mn to the n minus 1 Cn. Okay, so you see that you get n equations starting at 0 up to n minus 1, and n unknowns. So given that, since the mi's are distinct, since the roots are distinct, okay, so if they're general enough, right, then you get m equations and m unknowns. M unknowns. So really, you have to check that these are not linearly dependent, right? But let's just assume that, okay? All right. So that's the idea. So that you could have to potentially deal with repeat roots and things like that, but let's sweep that under the rug for now. Okay? So this shows, right? This shows. So there exists some C1 through Cn, such that C1y1, or sorry, C1, so that y t is equal to C1 e to the m1t plus Cn e to the mnt satisfies star. So these are what are called the initial conditions. So you can prescribe them, or you can ask them to be given. Okay? All right. So we have that. So note that if let's say w of t is another solution, so it has the same initial values like that, then y of t, so then you'd say like this, y of t minus w of t at t is equal to 0. So this looks like y of 0 minus w of 0. This is equal to S0, minus S0, which is 0. Similarly, y prime of t minus w of t prime at t is equal to 0. This is S1 minus S1, which is also 0. Okay, and then you could continue going like this. And you have that, this all the way to n minus 1 of t minus wn minus 1 of t. T is equal to 0 is equal to 0. So what we've done is we'll take this. So if we take two solutions that satisfy the same initial value problem, right? They have the same initial conditions. You get one where you get the same thing, but we can assume that all these things are 0. Okay? So it'll turn out that so what you need to do is, so to show that the solution is unique, we need to conclude that we get the 0 solution. 0 solution, if we take, so 0 solution meaning that the function will be 0 if we take okay? So let's do, maybe we can do this in an example. So for example, okay, and then let's do this in the 2 by 2 case. Okay, so okay, so we could have something like y of t is equal to e to the m1t. So let's say it's c1 m1t plus c2 e to the m2t. And then we'll have, okay, so suppose this, okay? Also suppose that y of 0 is 0 and y prime of 0 is 0. Okay? So let's see what happens. So this is what happens when you take two solutions of the same, that have the same initial things, and you subtract them. All right? So let's subtract them. So let's say the y0 is equal to 0 condition, right? This gives us that 0 is equal to c1 plus c2. Okay, and the y prime of 0 is equal to 0 condition tells us that 0 is equal to m1 c1 plus m2 c2. Okay, so we have this system of equations here. Okay, so this tells us, so hopefully I don't need to add an extra condition, but let's see what happens. Okay, so c1 is equal to negative c2. All right, and so that's from the first equation. Okay, and now we can plug this in. So 0 is equal to m1 minus c2 plus m2 c2. Okay, and so this is equal to m1, let's say m2 minus m1 c2. Okay, since we supposed, so this is why I'm saying that you have to deal with stuff when you have repeated roots. But since we supposed m1 is not equal to m2, right, this thing here is not 0, which implies that c2 is equal to 0. Okay? And using this equation here, this implies by this thing that c1 is also equal to 0. So hence, you know, when you have the 0 data, right, you get the 0 solution. So we get, so you know, okay? So the difference of those two guys is 0. I'll let you guys, let me let you guys catch up for a second. Okay, so let me recap. Okay, so the recap is as follows, right? So, one, we showed that there exists C1 through Cn complex numbers such that for S0, S1 through Sn, right, the function y of t is equal to C1 e to the m1 t1 t Cn e to the mn t solves the following problem. So we have our differential equation. Plus a0y. And then we have the initial conditions. We have the initial conditions, and we have n initial conditions. Y, and then we had the nth derivative, n minus first derivative, Sn minus 1. So this stuff here is what I called star, and this is what's called the initial value problem for a differential equation. Okay? And so we showed that there exists these, we can solve for those constants. We showed that 2, this is what I showed the last, was that if S0 is equal to all the way to Sn is equal to 0, then C1 through Cn are also 0, which implies that y of t, which is this thing, is the trivial solution. So, okay, so given, the last thing was that given y of t and w of t, so given w of t, any solution of the initial value problem in star, then, or in 1, okay, so we have anything like this, not necessarily looking like this, any function in the world, okay? Then this thing here, minus y of t, solves the initial value problem of, let's say, here of 2 with, i.e., with trivial data, with zero initial data. Okay, and hence it's 0. I guess I need to show that the 0 solution is unique, but okay, so I'll punt for that for now. So maybe I'll say something about this in a little bit. But this is kind of the procedure for uniqueness. Does this make sense? More or less? Okay. Okay. All right. So let me say some other things. So I'm going to say a little bit about, okay, so let me talk about eigenvectors real quick. So just some general things about eigenvectors. Okay. So I'm sweeping something under the rug here, by the way. So I just wanted to say the uniqueness for zero solution. For the zero initial data. Okay, so all right. So let me just say what let me just say something. So definition. So I think I said this informally. Did I state the official definition of what an eigenvector was? Eigenvalue. Okay. So let V be a vector space. And let T. Have you guys seen this notation? So this is a linear transformation from V to V. Okay, so it's like a matrix or differential operator. Be a linear operator on the vector space V. Okay, so a vector V, let's say a non-zero vector V, V in V. Let's give these guys. So sometimes this will be a function space, and sometimes this will be like c to the n. Okay, so this is general. Okay, so a non-zero vector V is an eigenvector for T, provided T of V is equal to lambda V for some lambda here. Let's say it's a complex vector space, okay? So for some scalar here. Okay, so all it does is it translates this. And so the value lambda is called the eigenvalue. So eigenvalue. Okay. All right, so let's do some examples. V is C infinity of, let's say, R to C. So these are functions from R to C. So these are like solutions of your differential equation, okay? So T is d dt, okay? And then V here would be like e to the mt, or let's say e to the lambda t, for lambda, a complex number. Okay, so then note that TV is d dt of e to the lambda t is equal to lambda e to the lambda t, right? And so this is equal to lambda v. Okay, so v is this function here. Okay, another situation you can have is where we have a matrix, a particular matrix that we could look at. So let me give you another example that's maybe more familiar. Okay, so let's do an example. So if A, let's say T, we'll say to be this matrix. Oh, let's say what V is. V, let's be C2. Okay, so these will have column vectors in it. Okay, T will be this matrix minus 2, 1, 0. Okay, then we can have, say, C, or well, let's do V. Let's keep this notation. I'm going to do a vector like this now. Okay, minus 1, plus 1, 1, like this. And then we'll do lambda. So this is going to be minus 1, plus 1, like this. Okay, so let's check. This actually makes sense. All right. Okay, so this particular one here, so we're going to have TV. Okay, so this is, well, this is this matrix, minus 2, minus 2, 1, 0. Okay, and then we're going to take this vector here, minus 1, this is an I here. So that's not clear. So that minus 1 plus 1, minus 1 plus I. Okay? Plus I, and then we had what, a 1 here. Okay, we can just matrix multiply. Minus 2, minus 1 plus I, plus a minus 2 times 1. So this is another vector. And then we have a minus 1 plus I, and then plus a 0. Okay, and so let's see what this is. So this thing here is 2 minus 2I minus 2, and this is minus 1 plus I. All right, this guy, this is a minus 2I and minus 1 plus I. All right, and so let me show you something else. So let's keep doing this. So this thing, so let's note here, so like a little side work. So I want this to be an eigenvector. So, and we want it to be that thing. So we want it to be we want this times this to be this. Okay? So let's see what this thing squared is. So this thing here is 1 minus 2I plus I squared. So this is 1 minus 2I minus 1. This is minus 2I. Okay? So this thing here is minus 1 plus I squared minus 1 plus I, like this. Okay? And if I just bring this up here, so this is the same thing as minus 1 plus I of here. Now we have minus 1 plus I and 1 here. So this is equal to lambda. I'm doing these, all right? So this is an eigenvector. So we checked that this is an eigenvector for this matrix. Okay. So, great. So, okay. So, one question we can ask is, when does a matrix have eigenvalues in it? So there's two things. I didn't know which order to do this in. Okay. One thing is that when you have a basis of eigenvectors, how can you use that to help you solve differential equations? That's one question we can answer. The other question is, when do eigenvectors exist? Right? When can you have a basis of eigenvectors for a vector space in a linear operator? So there's two questions that I would like to address. So two questions. So I said the motto, right, is to expand things in terms of eigenvectors. Right? They're useful because, okay, why are eigenvectors useful? They make the operator act very stupidly, right? You apply it and it just turns into multiplication, right? And if you can use that to your advantage, you know, it's obviously simpler than doing some complicated linear operation, right? So two questions is that so given some v and t from v to v linear, when does a basis exist? A basis of eigenvectors for T. Basis of eigenvectors exist. All right, this is a complicated question, especially if this is a higher, like if this is an infinite dimensional thing, like if this is like a function space, that gets super complicated, okay? But we can answer it in the case of these things being finite dimensional vector spaces, right? The other question is, how can we use eigenvectors to help us solve differential equations? Okay, so I guess in the next class, I'm going to, I guess I'll answer these two questions, right? And yeah, and then we'll just continue from there. Okay, so the goal again is to kind of, we'll start to generalize these things after we get going. All right.